We'll start this video with a few more definitions to keep in our pocket, and those are going to be theory and law. This course is a magical mix of both what actually happens and what happens in theory, which is neat and exhausting. We won't harp on all of the theories that guide our study this term, but there are a few big players that you'll need to learn and keep in mind as you learn the rest of the content. All right, here's those few terms before we get to Dalton's atomic theory. A theory, often referred to in chemistry as a model, is some simplified picture that's used to help explain how something occurs in nature. Nature doesn't mean the wilderness here. Nature means how something would tend to occur or happen. So here's a small piece of lithium, and it's being added to water in the laboratory. The natural tendency of lithium in this situation is to react violently and potentially catch on fire. A theory is fairly broad so that they can cover a wider range of phenomena. Dalton's theory, for example, covers every type of atom that you might encounter. Given the size of our table, that's quite a few atoms, and this is a pretty narrow theory. Theories are formed after exhaustive use of the scientific method, which I'm sure was mentioned often in your previous schooling. Observations are made, hypotheses are developed. Experiments are conducted to test said hypotheses, and then, after careful review and analysis, models are built and/or theories are formed. If more experiments are performed and data or observations disagree with the model or even part of that model, it's adjusted and redeveloped. Rinse and repeat all of the times that might be necessary. This is how science, not just chemistry, came to be and will continue to come to be. The theories we will use in this class are pretty darn good. We're going on hundreds of years of observations in some cases, so most of our theories have more data points on their side than we can possibly imagine. But even so, a theory is just that. It's a really good guess based on the evidence that we have at the time, and sometimes more than one theory can come from that same evidence. Even with the very general and simplified things we will see here in this general chemistry course, there will be topics where different theories can lead to slightly different answers. While students love to go elsewhere for additional practice and explanations, you'll need to know the details of the theories that I subscribe to and present come quiz time. They're all backed up by text and not flat earthers, etc., so they're not too hard to buy into. Laws, on the other hand, tell us what will happen in specific situations, usually based on theory. Think of these as an if X, then Y situation. If you drop an apple, then it will fall to the ground because of Newton's law of universal gravitation, which is not to be confused with his laws of motion. The term law is not a measure of how good or bad some theory is. It simply states what will happen when a phenomenon occurs. Now, it's a fairly common misconception that once tested and proven enough, a theory then becomes a law. And this isn't true, as the two terms differ in what they're trying to do, and one does not lead to the other. A law is a set of observed facts, and a theory explains why those observed facts happen. Or theories explain the how or why, and laws explain the what. All of that out of the way, let's talk a little bit about Dalton's atomic theory. This theory was published in 1808 by John Dalton. Dalton had no formal education, but started teaching science at the age of 12. The theory was a major breakthrough at the time. Sure, now that we know a lot of other things, it seems like a fairly straightforward and almost elementary theory, but that's likely because so many ideas have been built directly on top of it. More asides. You're not in this class because you thought it might be fun to take a relatively difficult chemistry course for science majors at a major R01 research institution. You're in this class because you want to be a doctor, a dentist, an optometrist, etc., or because you're interested in research, or because you were poorly advised. In that latter case, you're currently terrified, and I'm so very sorry about that. But if you're going into science, you'll be asked to push boundaries, ask questions no one's asked before, and put ideas out there, including possible answers to questions that no one has asked that might seem cuckoo for Cocoa Puffs to some because they back a different theory. And you'll have to be thick-skinned enough that you can live through your theory being ridiculed, picked apart, and partially proven wrong. Dalton wasn't the first to go through this, and he certainly wasn't the last. Dalton combined his thoughts with other common ideas at the time and presented his theory in 4 postulates. You'll be responsible for knowing these postulates and being able to identify them as part of Dalton's theory or not. You'll also need to be able to speak to which of the postulates have been proven fully or partially incomplete. Don't worry about numbering them or memorizing them in any order, as they're presented in different orders depending on where you find them. And sometimes there's even a fifth one because they're divided up differently. Worry about the content here. The postulates are presented in more detail in our text, but the first one, which states that all matter consists of atoms, incorporated ideas presented more than 2,000 years earlier by Democritus. Dalton went on to say that these atoms are tiny, indivisible particles that are the smallest thing that can participate in our chemical reactions. A second postulate states that atoms of one element can't be turned into atoms of other elements. This flew in the face of alchemy, which was a popular, albeit impossible, idea at the time. Think law of conservation of mass here. Thirdly, Dalton incorrectly stated that atoms of one element are all identical, including in mass. At the time, the idea of isotopes hadn't been published, so it's less that this is incorrect and more that it was just mistaken. And lastly, Dalton stated that more than one atom can come together in some permanent combination to form compounds. That newly formed compound will have a set of properties that differ from its constituent atoms. Dalton's theory was revolutionary and shifted how we thought about atoms, elements, and even matter. But as more observations were made and more data was collected, some of the postulates proved to be incomplete or even incorrect. The discovery of isotopes, or atoms that contain the same number of protons, making them atoms of the same element, but a different number of neutrons, making them different types of atoms of the same element, meant that one of the postulates was incomplete. All atoms of an element will contain the same number of protons. As we'll see in a later subsection, the number of protons define what element you have. So this means that this third postulate was partially true. But since neutrons have mass, and the number of neutrons can differ between atoms of the same element, this means that the third postulate is partially untrue. Isobars, or elements that share an atomic number, more later, also prove part of Dalton's theory incomplete. Since isotopes of different atoms can result in atoms of different elements having the same mass of subatomic particles, it isn't actually true that atoms of different elements have to be different in all respects, a claim that Dalton made. But even with the same atomic number here, the atoms will have different properties. So even in this case, we can't entirely discount his theory. Nuclear reactions can involve the transformation of one nuclei into a nuclei of a different type. So atoms actually can be changed to atoms of a different type. And lastly, if you'd really like to split hairs, technically atoms can be broken down into their subatomic particles, which means that they aren't the smallest thing that we can get to. But they are the smallest thing that we can get to that behaves like the sample they're a part of. So I don't really count this as an argument against Dalton's theory. Some do though, so I included it here. Dalton's postulates help to explain the mass laws that govern much of what we will do in this course. The first is the law of conservation of matter, also called the law of conservation of mass. It states that matter can neither be created nor destroyed, simply changed in form. And yeah, there's the Einstein thing where a slight bit of matter can potentially be changed to energy. But that amount is so small that we're not going to complicate our discussion with it. Instead, as we study reactions, we will remember that the mass of a substance won't change in any meaningful way during that reaction. The number of pieces may change and their properties must change, but the total amount of matter in a process must remain constant. While Lavoisier first stated this law based on his combustion experiments, Dalton's postulates that state atoms have a fixed mass, cannot be created nor destroyed, and cannot be converted into other types of atoms helped to support this law. 3 out of 4 isn't too bad. The second law that will guide a lot of what we do in this term is the law of definite proportions. This states that every particle of a particular compound will always contain atoms of the same elements in the same ratio as every other particle of that compound. For example, nitrogen monoxide will always contain a single nitrogen atom and a single oxygen atom covalently bonded together. If, for whatever reason, we start talking about NO2 or N2O or N2O4 or literally any other ratio of nitrogen and oxygen atoms chemically bound, we are now talking about completely different compounds that have completely different properties. Dalton's theory that a compound is a combination of a specific ratio of different atoms, each with its own mass, supports this law. Again, multiple postulates in his theory help to explain this natural phenomenon. This law is important when we begin calculating the fraction by mass and the percent by mass of a compound, because the fraction by mass of an atom within the same compound will always be the same. But when we change the ratio, the fraction by mass changes and will have to be different from the other ratios. The last law you need to be familiar with is the law of multiple proportions. Dalton stated that when two types of atoms come together to form a compound, the ratio of the masses of those two atoms can be written as a whole number ratio. This is essentially the beginning of our chemical formulas. Now, if you haven't gone through section M.1 yet, the chemical formula thing might not make a ton of sense. It's described in more detail there. But in short, we write our formulas with the symbols for our elements, followed by a numerical subscript to indicate how many of that element are present in the ratio. Those subscripts follow the symbols. No number is present, that subscript is an implied 1. The NO we saw earlier has a 1-to-1 ratio of nitrogen atoms to oxygen atoms. NO2 has a 1-to-2 ratio of nitrogen to oxygen atoms. N2O a 2-to-1 ratio, and N2O4 a 2-to-4 or again a 1-to-2 ratio. If you calculated the mass percent of nitrogen and oxygen separately in each of these four compounds, which you'll actually do in a later section of Module 1, you get different values for each of the compounds that have different ratios. Note that NO2 and N2O4 have the same ratio despite being different compounds, so the percent composition cannot be used to differentiate these two. Since the ratios and percent composition is different, each of these compounds will behave differently despite having the same atoms. Know that not all atoms can come together in different ratios. As you'll see in the nomenclature module, molecules are comprised of non-metal elements which share electrons when they come together. These elements can come together in different ratios and form multiple compounds. But if you have ions that come together, they can do so in one and only one way. You might be wondering what you need to do with all of this theory. The short, amazingly unpopular answer is you have to learn it. Theoretical material such as this makes great multiple choice or theoretical style questions. I can test your general science literacy by asking what wasn't included in Dalton's theory and what hasn't been deemed incomplete since its publication. Since laws describe what will happen in a given situation, it's easy to include these as in practice questions come quiz time. So all of that to say, never skip the lots of words sections of the course. When you're taking notes, try to reword information from the videos and the text as much as you can so that it makes sense to you and is easier for you to study. If you're worried that your rewording might not be sufficient or might have made something false, your TAs and I are more than happy to read over your notes quickly and let you know how you're doing.